Hello everyone, welcome to Vyas Certification Kota. In this session, we are going to discuss class 12th chapter number 6 Electromagnetic Induction. Clear? In this session, you will find detailed video solution of each and every question of NCERT and exercise. Clear? As well as you will find some key concept behind that question also. Clear? So now we are going to discuss every question here. So concentrate on a screen. Now dear student, we are going to discuss question number 6.1, and in this question it is given to you, predict the direction of induced current in the situation described by following figure. Clear? So actually in this question from figure number A to figure number F, total these figures are given to you, and now we have to find what is exact direction of induced current in each and every case. Clear? So first of all, let us try to understand concept behind this question. Clear? Actually we know whenever there is some change in a magnetic flux is to be taking place, it means I can say whenever there is some change in magnetic field lines that will taking place, at the time we can say according to Faraday's law of electromagnetic induction, an induced EMF is generated. Clear? Whenever an induced EMF is generated, at that time I can say if a circuit is closed, an induced current will flow. Clear? So I think concept is very clear to you. So concept is very simple. Whenever there is some change in magnetic flux, induced EMF will be generated. If circuit is closed, induced current will be produced. Clear? If we talk about direction of that induced current is determined by Lenz's law. According to Lenz's law, the direction of induced current will be like this. It will try to decrease the effect. Clear? Or it will try to decrease that factor due to which that current is produced. Clear? It means I can say overall it will oppose the magnetic flux. Clear? So now we are going to discuss this case. So first concentrate here. For this is figure number A. In this question it is given to you, we have a bar magnet. Clear? And this bar magnet is coming to near to this coil, and this coil is at rest. Clear? Now we know whenever there is some relative motion between this coil and the bar magnet is to be taking place, definitely magnetic field lines that is associated with this coil, this changes. Clear? Now you can see if we talk about this case, this south pole, or we can say this bar magnet is coming near to this coil, at that time I can say the magnetic field lines that is going out from this particular area that increases. Clear? It means I can say here definitely an induced EMF will be generated because magnetic field lines is changing. It means I can say magnetic flux is changing. Magnetic flux is changing, it means definitely induced EMF will be generated. And because you can say here this circuit is given to you, this is closed, it means induced current will also be developed. But what will be direction of induced current? So I can say direction of induced current that is given by like this, that it will try to decrease these magnetic field lines or this magnetic flux. So now you can say if you see it carefully, you can say if we let's suppose this induced current will flow in this direction. Clear? At that time you can say if you curl your finger like this. Clear? If you curl your finger like this, the direction of thumb, it will indicate direction of magnetic field. Clear? So at that time I can say due to this induced current, magnetic field in this direction increases. So definitely it is opposing this case. Yes or no? It means I can say if we talk about direction of induced current, so this current is actually flowing like this. It is going through this one, and again coming to this point. Clear? So what is direction of induced current? Directly I can say direction of induced current, this is given by from Q, R and P. Clear? So we have Q, R, P and again Q. Clear to you? Current is flowing in this direction. If you are looking from this side, from magnet side, you can see the direction of this current is clockwise direction. Clear? So now we can say Q, R, P, Q. This is direction of induced current. Clear? So this is all about part number A. Now we are going to discuss this figure number B or the part number B, and our objective here is to find what is direction of induced current, clear. Now you can say again we have a bar magnet, clear, and this bar magnet is approaching to this coil. So definitely I can say, because this is south pole, so magnetic field lines that is going through this section, that is increases, yes or no. So at that time I can say induced current will be developed in this section or in this circuit, like this it will try to decrease this effect, clear. So again I can say here, if I say this induced current will be like this, yes or no, clear. So now you can say, if you curl your finger like this, thumb will indicate in direction of magnetic field in this direction, clear. But because south pole is coming near to it, definitely magnetic field lines is also increasing in this direction, clear. So I can say this induced current will try to decrease the effect of that factor due to which it is we can say generating, or we can say it is producing, clear. So directly you can say, if you see this current is actually going like this, and it is going from P to R and then Q, clear. So direction of induced current I can say this is PRQ, PRQ, and again I can say that is P, clear. So now if I say for this circuit, clear. Now you can say in this situation for this coil, you can see this bar magnet is actually going away from this coil, clear. So when this is going away from this coil, definitely because this is a north pole, again I can say from north pole magnetic field lines always going outward direction, clear. So as north pole is going away from this coil, definitely magnetic flux decreases. Magnetic flux decreases, it means I can say induced EMF will be generated, and induced current direction will be like this, it will try to increase this magnetic flux, clear. So at that time again I can say here direction will be generated, it will be like this, this is direction of induced current, clear. Now you can see, if you see from this side, if you see from this side, you can see that this induced current in anti-clockwise direction, here this is in clockwise direction, in this case I can say this is anti-clockwise direction. So in anti-clockwise direction, if you curl your finger, definitely magnetic field lines, it will be a magnetic field direction is this one, clear. So from here we can say actually this is going from Y, Z and X, clear, Y, Z, X, and again you can say that is Y, clear. So this is direction of induced current for figure number B, clear to everyone? Yes. Now we are going to discuss case number C. In this case it is given to you tapping key just closed. Initially we are assuming definitely here we have a coil, clear, and we can say here we do not have any relative motion, clear, but it is given here first this tapping key is open, clear. It means I can say initially this is open circuit, but what will happening at the time this tapping key is just closed, clear. When this tapping key is just closed, definitely I can say direction of current that is increased, I mean magnitude of this current that is increases, clear. So now you can say if you are taking this as a front section, clear, if I am taking this as a front section and this one is a we can say bottom one, clear. Now if I am looking from this side, actually this you can assume, actually you can take this one as a behind one and this one is front one, clear. So now you can say from this side this is actually in clockwise direction, clear. In clockwise direction it means I can say if I curl my finger like this, listen carefully, if I curl my finger like this, at the time I can say magnetic field in this direction, clear, because current is increasing, so I can say magnetic field lines is increasing in this direction, clear. So in this coil current will be generated like this, it will try to oppose these magnetic field lines, clear. At that time I can say definitely this current will flow from this direction in anti-clockwise direction, clear. So if you curl your finger like this, thumb indicate direction of magnetic field, and definitely direction of this magnetic field is in this direction, so it will try to oppose this effect, clear. So now what is direction of induced current in this coil? So I can say here this is Z, X, Y, Z, clear to everyone. So this is all about part number, or we can say part number C, clear. Now we can say this is part number D, and in part number D it is given to you rheostat setting being changed. So let's suppose initially we have somewhat resistance. Let's suppose I am saying resistance value is decreasing. let's suppose I am saying resistance value is decreasing. As resistance value decreases, at the time current that is flowing in this coil, that is decreases. Clear? I am assuming this side is the front side and we can say this is behind one. Clear? Now if I observe from this side, you can see here current is actually flowing in a anti-clockwise direction because you are decreasing resistance. Clear? So if you curl your finger like this, it indicates direction of magnetic field. Clear? So magnetic field direction we have in this direction. Clear? So definitely I can see the magnetic flux that is related to that coil, that is also changes. So whenever there is change in the magnetic flux is to be taking place, I can say induced EMF will be generated, and because this circuit is closed, so we can say here induced current will be developed. But this induced current will be developed like this, it will try to oppose this coach. Clear? So at that time I can say this current will be flow like this. Yes or no? Because if you see from this side, you can see this is in clockwise direction. Clear? So if you curl your finger like this in clockwise direction, thumb indicate direction of magnetic field, this one. Clear? So from here you can say clockwise means I can say clockwise. Yes. So current is actually flowing like the Z, Y, X and Z. Clear? Actually some student may say, sir, I am observing this is a backward one, this one is front one. So somewhat there may be confusion, but if you are taking one direction, let's suppose if you are taking this direction as anti-clockwise direction, if you are looking from this side, at that time you can say current that is produced in this coil in the clockwise direction. Clear? Because here we are actually decreasing resistance, that's why current is increasing, so it will try to oppose that current. Clear? So I can say here the direction will be Z, Y, X, Z. Clear? So this is all about part number D. Now if I talk about part number E, in part number E you can see tapping key just released. It means we can say initially, let's suppose this is a closed circuit and a particular amount of current that is already flowing in this circuit. Clear? But what will happen when we just release this tapping key? Just release means I can say value of current that is decreasing here. Yes or no? And you can say current is flowing in this direction like this. Current is flowing in this direction means if we observe from this side, if you observe from this side, you can see this is in the clockwise direction. Clear? So now if you curl your finger like this, magnetic field in this direction. Clear? It means I can say magnetic field lines that is associated with this coil, it will be like this. Clear? At the time, because value of current is decreasing, so I know if you are taking this as a solenoid, for solenoid I can say B, this is equal to mu naught Ni. So I can say when I is decreasing, clear, at that time magnetic field value is also decreasing. Clear? When magnetic field is decreasing, it means I can say value of B decreasing, it means magnetic flux decreases because flux is given by B dot A. When value of flux decreases, again I can say whenever there is some change in the magnetic flux is to be taking place, I can say induced EMF will be developed, and because circuit is closed, induced current will be flow. Clear? So at the time you can say current will be flow in this direction, it will try to increase magnetic field. So again you can say current will be flowing like this. Now you can say if you observe from this side, you can say current is flowing in anti-clockwise direction, also in the clockwise direction. Clear? If you are observing from this side, this current will flowing in a clockwise direction. You can say this is backward one, this is front one. Clear? So in clockwise direction, what is direction of magnetic field? In this direction. If you curl your finger like this, clear, like this, at the time we can say this is direction of magnetic field. So now you can say here we have direction of current X, R, Y and again X. Clear? So this is all about we can say yes. Clear? This is all about this part number E. Now here we have one more part. This is part number F. Clear? And in this question it is given to you. Here we have this. We can say this is a current carrying wire. Clear? And this current carrying wire, and we have this loop. Clear? Now you can say due to this straight current carrying wire, if you find direction of magnetic field, what is direction? Clear? Now you can say if I place my thumb in the direction of current, this curling finger represent direction of magnetic field. So now you can see here you will find magnetic field lines that is in the same plane of this coil. Yes or no? You will find magnetic field lines in the same plane. Clear? I can draw it like this. This one. Clear? Clear? You will find here direction of magnetic field like this. Clear? So now you can say these magnetic field lines are parallel to this coil. Clear? And I can say these magnetic field lines will not passes through the area of this coil. It means you can also say like this flux. Flux is given by that is B dot A. Clear? Or we can say this is equal to BA cos of theta. Clear? Now theta is what? Theta is an angle between B vector and A vector. Clear? So B vector you can say here we have tangential direction and A vector that is perpendicular one. So angle between magnetic field and area vector we have 90. So I can say this is given by BA cos 90. Clear? And you can say here this value 0. So magnetic flux that is associated with this coil is 0. So whenever there is no flux, I can say there is no induced EMF and no current, no induced current is produced in a coil. Clear? So I can say what is answer of this question? No induced current. No induced current. Clear? So this is all about this question.